So obviously my name is Marc Parisi. I'm an employee of Hortonworks. This is multilingual communications using Accumulo. That link you see there is a link to the bibliography for this. It has a link to the code, link to the GitHub, link to some sites that I've linked inside the slide. So you can go ahead and go there now if you want. If you find bugs in code, please don't bring them up. So I'm a PMC member of Apache NiFi, also Apache Accumulo, but I've worked a little bit less with that in recent times. I'm a serial website owner. I own IoT All the Things. I'm most proud of that site. Last year I had an issue in this room where it kept going because I recorded myself in presentation mode doing a time before, earlier in the day, and it was going through and reproducing that. So it sounds like I might have some more flickering and issues. Today we're going to talk about a client I built over about 4 years, around April of 2012 to June of 2016. It is an entirely native client. By native, I mean it's written in C and C++. I'll go through the history and why I made that, the design, where it differs from the standard Accumulo client. In this client, we can do anything from accessing Accumulo services, writing R files, etc. And we'll go through some comparison of different techniques, primarily using the proxy to do these same communications. And we'll talk about the differences. As I mentioned, I started this in around April of 2012. This was, I believe, a month after Accumulo was moved from incubator to a top-level project. I could be making that up, but it's around that time where I decided, let me try and learn some of the internals to the Accumulo client, to Accumulo itself. I started in C and migrated to C++. How many are familiar with C++? Okay, so you know that's a really bad idea when you do that, especially if you're going from C to what are newer standards with C++ 11, 17, 20, etc. The intent of this was actually to connect to multiple key value stores. So we have HBase, Cassandra, and now I do have connectors for Redis, and we'll go through why these exist. In 2018, I started thinking about integrating some bindings for Python. I have later today, I'll try and post the one I have for Ruby. We can use PyBind and bypass some of the C bindings that we'll talk about. And there's also Golang, where we can simply just run the C code directly. So these are some of the questions I think that I get when I mention this. For those of you who I haven't mentioned it, the project's actually named Sharkbite. So if you're familiar with the Sharkbite connectors for plumbing, that's where I stole that. I apparently am infringing on trademarks, but thus far no one has actually cared. But I'll go through the why, the purpose of what some of this is, and discuss why not use the proxy. Hint, you probably should. So the real reason, I think it's safe to say that whenever you say you've written something in C and C++ versus Java, most people think, oh, it's going to run faster. That is almost never true. In most cases, when you do that, you're actually, especially in the case of any type of key value store, the primary bottleneck will be I/O. And we'll go through that in a little bit of detail. But when I first made this, I had some ideas. This was back in 2012. I thought, well, can we do something which I call Colossus? That code is in a private repo, and part of it exists in the code base now, but the intent was to bypass the tablet server and actually take many of the communications as a proxy for the tablet server and direct them to the tablet server when needed. In addition to that, hedged reads, which are effectively, at the time, R file communications are significantly faster in C++, and I'll go into why. But doing hedged reads and going to both directions. So I did that in 2012, and some of that code still exists in Sharkbite now. So this was, I think, Accumulo 1.3-ish, where I started implementing this system I called Colossus. The intent of this was mostly to avoid some of the bottlenecks of doing communications with the tablet server. In many cases, we can do memory access much faster, much better, and more eloquently, I think, in C and C++, not to sound elitist. Memory access could be controlled. We could do caching in a much better way outside of a JVM heap. Any of you who have ever had JVM and GC issues, we can avoid that entirely, unless we write bad code, which I generally do. But then most things like memory maps and memory maps were kept in C and then forwarded to the tablet server. Master communications were also redirected to the tablet server process that was much smaller on the system. And because there is a native C++ R file reader, we could do that within the R client and sort of piggyback on these ideas. And that the goal was to avoid Java communications as much as possible, minimize those, and go to the client. There was a lot of promise in this, but to be frank, it's incredibly complex. The whole paradigm was something I wanted to try, and that's sort of the impetus for why I built some of this code. Furthermore, I saw this as a great way to build my skills back up in C and C++. So it was really, this was more trial and error. So what exists now is less of Colossus, more of a standard client. And we'll go into some of that in a little bit. Hedged reads are effectively a combination in a client that does RPC scans. So in this client, we do direct communications to tablet servers through Thrift. A functor sort of also works in tandem to scan R files. This worked with Colossus with in-memory maps, but right now we don't really have that capability because Colossus doesn't really exist. So therefore, what exists now misses some of the in-memory maps. So it's more suited for read many, write once. Even this little tidbit toward the end, R file reads being faster, that's not true because it still is 3 to 5 times faster to read an R file, but it's also about 3 to 5 times now faster to write an R file. And that's primarily because of the dependencies of libhdfs3. It's improved dramatically over the years. And in many cases, we avoid a lot of the bottlenecks for compression, decompression of these data blocks that were mentioned earlier. I think, let me set the groundwork that I think using C++ generally as a client is a bad idea. The number of people that rose their hands because that they knew C++ well were few in this room. And I think the community as a whole, within Accumulo, if we move to something like this, we'd be unlikely to maintain it. So this is an example of template metaprogramming. This is actually a very simple example. Substitution failure is not an error, is a paradigm within C++ whereby we're doing more compile time generics, implementing features in compile time as opposed to runtime polymorphism that we typically see with generics. This is something that's been greatly improved in C++ 11, even more so in 14.17, and the standard committees is doing great work for C++ 20. So this reference is Accumulo 1.3. That's because I made this slide years ago. Nothing has changed. The same model of data distribution is effectively the same. What's important, I think, to point out here is that within the client, since the intent was to interrogate multiple sources, with the exception of something like Redis, most of these systems have a data distribution model that's relatively simple, or similar rather. We have data stored either in tablet servers or region servers. They're generally relatively the same. We go to some source, such as the root master, to get locations. We go to the servers to get the data itself. These paradigms are relatively similar, and nothing has changed between the Java client and Sharkbite client. The differences are in implementation. This goes into some detail about how these abstractions exist for these many different services. So the idea behind this was that there are many layers of interconnect of compile time generics. And that was an important point that I wanted to implement, in that I felt if we wanted to institute some connector to HBase or Cassandra, then it would require either we do some type of runtime polymorphism or we're discrete about our template metaprogramming. So constructed types are passed via templates. Almost everything is a form of template metaprogramming. So as I mentioned earlier, SFNA, that's a concept which is a relatively simple C++ concept that enables us to try out different types effectively at compile time. This also enabled me to create a feature that does object translation of key and values at any different point in the client. So for example, many people talk about unstructured data. I think that is not really a concept that's real. I personally think that all data has structure, you just have to apply it. And the concept here was that we can do object translation along that route, whether that's as we get it from the tablet server or in a client as we're merging data from multiple sources. Someone once asked me, why do we need this feature? We have Presto. Well, Presto was developed much, much later than this feature was. This was developed early 2012. I think, I don't want to assume when Presto began, but looking at the GitHub, it was developed much later than this piece of code. So this isn't really anything novel. Google primarily has done these types of things with their code bases, and they mentioned it in their papers. This was just an implementation of something I've found useful to do object translation on data as it arrives with injected code that is compiled at compile time. Here's an interaction kind of at a glance. I realized I had a lot of text, so I decided to make a picture. In this, we can see that if you go to the website and look at any of the example code, the Accumulo connectors are obviously predicated upon Zookeeper. We have some type of master connection. In this case, it's called master connect. RPC calls, again, are all abstracted through template metaprogramming. We can inject multiple connection points at any time in your development process. We create the scanner, we interrogate from the different servers, and we have those translated object I call variadic messages. All this is returned to the client, and we can perform translation of key values at any point. It's not too dissimilar from what exists in Java, but I would say that many of the design decisions that I made were based on the Java client in obviousness because I was working on both. I wanted to learn Accumulo more, so it stands to reason that why not take a good design decision? And most of what I've taken is mostly from Accumulo. So there's not a lot of, most of the changes are in the details. So after the next few slides, we'll get into some comparisons of the different types of languages and connection points to different languages. But the interconnect layer is, if you end up going through the code, that's effectively what does the connecting point, it is the connecting point to different services, whether that's the master. The goal here was to sort of reduce the amount of code. I think if you go through Accumulo code, there's a lot there for different connections, different types of pooling, thrift transport pool, all these different connection points. And a lot of this can be done a little bit more simply with template metaprogramming if you're familiar with it. Alluding back to the previous point, if the developers aren't familiar with it, it's actually significantly more complex. But this enabled connections and connecting points to different services it made it much more seamless and improved the amount of code reuse between the key value stores. The amount of code differences for Cassandra were relatively very small, to the point where it was just one or two classes with translations over to keys and values and doing whatever was needed. But there was very little code implementation for the different services. And that was mostly the goal with Sharkbite, given its name. The next feature that is somewhat unique are connection heuristics. These are user-defined functions for how to interrogate ranges. The utility of this has been mostly multiple clients can, at any point, interact with each other to corroborate how they're going to scan Accumulo. There's the point clients can and should interact. I think if you have 20, 30 different clients, we should not make the assumption that they all need to go to the master or to the root, to the master, to the tablet servers. They should work together in some way. So the point here was that we could inject multiple things. One could be memory caching, shared memory to share details, assuming we could still apply a visibility filter, a security, et cetera. Or we could just simply make the assumption that the ranges we're scanning, we're not going to interrogate the same tablet server at the same time. This was something you could simply embed into your scanner. Doesn't really work exceptionally well with writes, I've found, but with scanners it can work so that all of these services, whether they're different clients, different writers, et cetera, maybe they're creating R files, can all communicate with each other if needed. The goal was to avoid T-server overhead and also facilitate hedged reads, so that there's no point interrogating an R file twice if the same scan comes in. It works significantly faster in this case than caching in the T server. In most cases, we could leverage different caching technology outside of the tablet server in the clients if we need to. So is this really any better? You have one person writing a code base versus many. So just from that standpoint, I would say no. But we do have some improvements. We could potentially avoid proxy, which could be beneficial. We'll look at some examples in a little bit. But we avoid some of the RPC costs, which Keith mentioned earlier. You certainly avoid that, and we do have a market improvement in performance, but you have to kind of balance that with maintenance of the client. I wouldn't say this is necessarily better than the Java client. There are memory improvements, some speed improvements, but in general, development of this really hasn't kept up. It works with 1.9, but it won't work with 2.0. And in many cases, that's fault of thrift generation of code. There's a small piece of the code that interacts directly with thrift. That code regeneration is poor at best. So I'm not sure if people using the proxy for C++ have run into issues, but the generation of the code is almost always compile time valid, but functionally incorrect. So let's take a closer look at some of these items, especially in regards to the proxy. As I mentioned, there will be additional RPC calls, but this can be load balanced. So I think the nice thing about the proxy is that first and foremost, we kind of avoid language elitism. Many people who write C++ look poorly upon Java for whatever reason. Many people that write Java look poorly upon Pythonists. Those hate Rubyists. I don't quite understand it, but it's true. People make the assumption that C++ is better. It isn't. I think that's easy to get past, but you can write bad code in any language. I managed to do it in at least 4. I don't write Python, so the Python code you see that I've written, be forewarned that it is bad. This was the first piece of Python code I've really ever written. But let's look at some examples. In this, as I mentioned, this is written in C and C++, and I say that because there's a specific layer of C that does translation from structs to classes and objects, and that's because I wanted to better facilitate language ideation so that anyone writing Python, we could use what's called PyBind 11, which does direct binding to C++, but not many people will and want to use that. Go is very easy to integrate with C, but not necessarily as easy with C++. RPC costs are about the same as any other client, save for the fact that you're avoiding the proxy, but you do incur a cost of the dynamic linking in addition to C types, which does the translation from structs in C to C++. That is not a zero-cost operation. It may not be big in terms of big data, but it's certainly a cost that you will incur. So many of the applications that I've written for this have been written on smaller machines, the Raspberry Pi, for example, where this performs much better. Starting a client on a Raspberry Pi or even my router is significantly more expensive. Many may argue, why would you do that? Because you still have to connect to Zookeeper, but I've worked on provisions to avoid that. So again, these connections to C++ are not actually native when we're doing something like Python or Go. I would argue that C++ in recent standards have made it incredibly user-friendly. I began the transition in 2016 to more smart pointers, which avoid concerns about allocation, freeing memory. Garbage collection is a little bit different in C++. In that, with recent specs, it's done by a paradigm called RAI, which is resource acquisition is initialization. That effectively means that when you enter your stack, you create your resources, you acquire them. When you pop, you do your recollection. And many in the C++ community think this is much better than external garbage collection. I'll let you decide. But this type of implementation where we're having a C connector to C++ will impact performance slightly, and we'll see that. I've made some improvements most recently, so as we'll go through some of the examples where I'll give you some performance numbers, some of them have changed. I wrote the examples that we'll see in front of us around the time when they sent out the call for papers. This is an example in Sharkbite Python. I'm not sure you can see it very well in the back or even the front. I'm getting older, so I can barely see it myself. But it's a quick example. You're writing data. This isn't, I took this and some of the other examples from Accumulo, carved them up, did some performance analysis, measured the keys values per seconds entered in, or written rather, and then read. Again, when we're going through this code, this is relatively similar to Accumulo, but none of this is going through a proxy. All of this is connecting directly to Accumulo. Again, proxy makes a connection to this external service, which I think is important to note. There is a major benefit to this in that you don't necessarily have to concern yourself with the actual distribution of servers. We're not going to a root to a master to get where the locations are. We're instead going to a proxy. So this enables us to load balance, I think, a lot better than you would with something like the client I presented to you before, or rather in the previous slide. But these connections are to that tablet, or rather to that proxy server, are themselves native. So in Thrift, you can take and create your bindings, create your C++ code, Python. The only downside, as I said, is it does very poorly with C++. To give you some insight, comparators are often completely invalid. So the generation of code is not correct at all for me when I rewrite or re-update the Python bindings. That's not exactly true. That there is a cost to these RPCs. Thrift is not necessarily as good as, say, other RPC protocols with performance, but we pay that cost no matter the client, so there's no point in really differentiating that as a cost. So here is, I stole this from Accumulo. I did not put a reference, I apologize. But you can see the code's relatively similar. The difference here is that there's a translation of these Thrift objects, and that's passed along. In the previous example, the objects themselves are native. They're created in C, translated to C++, and then sent to Accumulo. Another difference, of course, I think the most important, is that we pay a major cost in Sharkbite for endian translation. Keep in mind, Java is big endian, and therefore, most communications, while they're also big endian, we have to deal with host ordering and translation. So that means every byte must be rewritten, potentially, or every integer, every long. All of those must be rewritten so that they're networked ordered, or big endian as Java. Go, I think, has much better integration than, say, Python, because it's able to do some compile time operations and deal with these C structures much more gracefully and almost eliminate most of that cost that you would pay with, say, Python. Ruby, I believe, has Rice. People write Ruby. Is that nobody writes Ruby? Wow. Okay. I'll admit I don't know it very well either, but I think there's something called Rice, which facilitates the C++ communication. So with Python, you have PyBind, which enables seamless integration between Python and C++. You have a much lower cost to acquire and to send that data. The important aspect here is that variadic functions are not supported, and this is something that's used within our API. That's something that has to be resolved. I think it's also important to point that the reason why there is a C layer is because of the way that C++ does munging at compile time. Those symbols won't be named something that you can necessarily always assume are valid. The point of that is that if you do something like the class loader in Java, you can expect your symbols to be named something. In C++, you can't always assume that in your symbol table. Therefore, generally you have to have something like another language construct do that translation, or in my case, write C code that does that translation. So in a minute, we'll go over some performance numbers. These were tested on my trusty R710. It is a heavily overloaded machine, or heavily loaded machine. I bring that up because all of these numbers have to be taken with a grain of salt. I didn't stop any services. I ran it 100 times, so I think after the 20 or 30th time of running it, I realized everything was running on that 710, so I didn't want to restart my tests. I am, if in a word, lazy, so I didn't want to go back and redo the work. 3 servers, 2 tablet servers, 32 gigabyte VMs, no special configurations. This is a very, very important point that will make itself known in a few slides if I remember. The goal here was to write 10 million keys on a fresh table. Why? Because we don't want any type of splitting compaction issues to be different amongst the runs. So we drop the data. And we're not concerned with costs associated with splits because just testing raw throughput. Computed the average, and I failed all of my math classes, so I can't promise I did it correctly. So here's some of the numbers. If they seem low, they are. Generally, all of these can get much higher if I tune or optimize anything or if I add tablet servers. Again, a very low, overloaded environment or heavily loaded environment. Not the fastest disks. In the case here, it may seem like Sharkbite's a little bit faster. It can certainly get much, much, much higher throughput with some optimizations. This client was built with -0, no optimizations whatsoever, so I could do debugging. With 03, which is the most optimization, you could certainly it certainly goes much higher. But I think the most important thing to note between these is the memory footprint. While 320 megabytes is not a lot, I'm sure any of us can write a client that uses a lot more than that in Java. You will be hard-pressed to use the C++ client and go much higher than a few hundred kilobytes. And that's because of the paradigm of RAI. The Sharkbite Python was generally much slower. I can profile through various profiling tools to see what's happening since most of the code is in C. Most of that cost was spent translating objects. With some compile time optimizations, most recently, it's about the speed of a Java client. The proxy Python, Accumulo, obviously incurring the cost of a proxy server, memory footprint there. I don't think that's of great importance to us. We most likely don't necessarily care about that. You may, I don't know about your situation, but the memory size of that Python client was roughly the same across all of those runs. The slower speed was simply because I had a separate VM set up for the proxy, and that RPC communication was a cost. Don't read into this. This is one example where I could see an improvement. I could certainly write a Java client that gets much better performance. I could tune that tablet server. That is the most important thing here, is that we are limited, no matter the language we choose, by our tablet servers. We are I/O bound by our tablet servers. GC was not a limiting factor here because I wasn't really pushing that. I really wasn't attempting to. I think that I wanted to test mostly the fact that raw performance irrespective of GC. So I tried to avoid any type of pushes to ensure that I triggered GC. I think one issue that we sort of deal with maybe in the future, I'll put some performance numbers of why the R file reads and writes are so much faster. It's simply because you don't have that off-heat memory for the decompressors or compressors. You don't have that triggering problems. So in this example, I wanted to avoid anyone saying, oh, GC was an issue. We could certainly up the memory footprint of that Sharkbite client, changing how we're flushing data, how much information or data we're keeping in memory. But I didn't spend a great deal of time attempting to modify that because I could get adequate performance numbers by simply running a generic client with no changes whatsoever. Most of that cost was spent converting objects. So in the examples where I've run Go, don't see those costs, and we see numbers that are very close to the actual Sharkbite client itself. I think RPC costs, there's an asterisk here, I think they were impacting the Thrift client, and I didn't dive into details of why or how or whatnot. I just wanted to say, oh, Sharkbite's better, let's just move on. But maybe there is room for improvement. Again, one word, lazy. Perception, there may be the perception, and I want to diffuse that, that a C++ client is better. It is a different client. T-server configurations, tablet servers, always have a bigger impact than whatever client you're going to use. They're doing the bulk of the work. You will get the most benefit from tuning your tablet server, not from changing your language. You can accommodate other languages, but you must be mindful of the fact that whatever you're running will have costs to go between those languages. Do I think that we could possibly get better adherence across many languages and very easily accommodate other languages with something like this? Yes, I do. In conclusion, Sharkbite was created many years ago as an interconnect between multiple systems. Not everyone cares about that or even wants to use that. I've tried my hardest to ensure that we minimized whatever footprint through template metaprogramming to ensure that we don't pay costs of runtime polymorphism. And we'll see in the next slide why I did that. I guess this really isn't the conclusion. This is not ready for prime time, but it may facilitate languages better. With that, I will bring up this slide that no one will be able to read. Oh, it actually is readable. But at this point, I'll take any questions. I think the most important one, though, is at the bottom, thread context switch. Someone is what Keith was alluding to earlier. I think that is a very big cost that may be an important cost for you. We can eliminate that through async programming as well, but I haven't spent much time doing that. All right, there's nothing left on the right side of the screen, so any questions? Or lunch, okay. Oh, there's Keith. I see Keith. Of course I see Keith. He asked why it wouldn't work with the Accumulo 2, and that's because as of stepping up here, I've not tried it. If there were changes to the RPC interfaces, then it won't work. I have found that in some cases there were minor changes along the way that may have caused a recompilation of certain thrift files, but if there aren't, I haven't looked, if there aren't dramatic changes in those thrift interfaces, it will work. Anything else? I'm not sure if the food's out there, but at this point we can go out and see if it is there. All right, thank you.